impulse excitation is defined as a force applied over a very short or kind of infinite amount of time, right? So if we have our time plot here, and then we often kind of draw force here, right? We will have a response that looks like this, and this is an impulse, right? So we don't really have any time under our impulse, but we have a high force. However, to make it simple, let's just go ahead and call this 1, right? So mathematically, we have an impulse response function of 1, and that can be represented by the symbol delta. Right? And that is also going to be equation 1 on your sheet. Right? So that's number 1 on Laplace sheet. Right? So it's a very large impulse, right, over a very short amount of time. Really 0. We're going to just kind of consider it that it's over 0 time. So we can go ahead and solve the Laplace method for this, or solve for a input for this using the Laplace method. And well, we won't quite make it there. Let's go ahead and get started. So we can draw our equation of motion, right? mx double dot plus cx dot plus kx is equal to delta t, right? Delta t is our input, so it's going to go on the right-hand side. The Laplace transformation of this, let's just go ahead and let's not do it in standard form. Let's just leave the m out front. So we have m times s squared x of s minus s x of 0 minus x dot of 0 plus c s x of s minus x of 0 plus k x of s is equal to 1. Right? And that 1, again, is coming from our Laplace sheet, number 1. That makes sense. So, however, let's assume 0 initial conditions, right? So we have no initial conditions. Which is something that we can do now because we have an input into the system, so we couldn't do that last time. This becomes ms squared x of s plus cs x of s plus k x of s is equal to 1. So we have an x of s in each one of these terms, x of s, x of s, and x of s. Let's go ahead and just pull all of those out. And we have ms squared plus cs plus k x of s is equal to 1. Solving for this equation, right? We get x of s now. So we have x of s. Go ahead and divide this whole thing by the ms squared plus cs plus k. But we know from before that our ms and our k, we can kind of convert this back into standard form. So we're going to end up with 1 over m. We're going to pull our m out times 1 over s squared plus 2 zeta omega n s plus omega n squared. Right, so that should kind of at least conceptually make sense. we pulled out our m, and you're like, oh yeah, zeta omega n squared. Oh, I remember where those come from, right? We did that in homework. All right, so again, we can go ahead and find this in the table. Does anyone see it on the table? Yeah, so number 10. And so number 10 gives us that 1 over m omega d e to the negative zeta omega n t sine of omega dt is equal to x of t. Right? Again, as long as zeta is greater than 1. Which we had originally because we said this was an underdamped system. So, however, if we want to set zeta equal to 0, right, we could get the same solution here. It's just our e to the 0 drops out. That becomes 1. So x of t is 1 over m omega n now because it's not damped sine of omega nt. It's in the wrong place.